All right, good afternoon. Hopefully we will not have any technical difficulties today. Anyway, things have been running smoothly for the last two classes in my other sections, so hopefully we will continue the streak in a positive way. All right, just some things to mention, and we have concerning a polynomial function, and we have just going back, and we have for a polynomial function, and we have again, you have four scenarios regarding the end behavior of the graph of a function. And if we have if the leading coefficient, that is if the coefficient of the highest degree term is positive and the degree of the function is odd, we're going to have the end behavior to have at the extremes, where we will have running down to the left and up to the right. And now if we have an odd powered function where the leading coefficient is negative, you're going to have the polar opposite in terms of the end behavior, where we have, in this case, you have running up to the left and down to the right. So if you have an odd powered function, whether it's like involving x to the third, x to the fifth, or just x, you're going to have at one end it's going to be running up and the other end it's going to be running down. But if you have an even powered function, like the highest degree term is in, say, x to the 10th or x to the second, you're going to have, at both ends, you'll have either both running up or both running down. And if we have an even powered function where the leading coefficient is positive, the end behavior will be up to the left and up to the right. And a quadratic function where the leading coefficient is positive would be opening upward from the vertex. You have up to the left as well as up to the right. And again, if the leading coefficient is negative, and we still have an even powered function, like in the case if you have like a quadratic function where the leading coefficient is negative, you would have the graph to be opening downward, where you have down to the left and down to the right. And now the other week prior to spring break, okay, we have what we're in reference to turning points. And again, those are those combined maxima and minima. Maxima and minima. Okay, and the turning points, you have the number of turning points of f of x will be at most one less than the degree of the polynomial function. And another way of wording this is that the degree of f of x will be at least one more than the number of turning points. And just, okay, so for this particular part, now we've looked at zeros and multiplicities and then made the segue over to end behavior. And then I'm just going to sort of consolidate all these topics along with turning points. And just taking what we have as an example, just to tie these concepts in together. And we can say, for instance, okay, say we have so you have determined the sine of the leading coefficient, the number of turning points, and the possible degrees of f of x. And we'll say that we'll start out with the function. Okay, so I'm going to provide a graph. In fact, I'm going to put up a couple of these. Okay, but let's say that we have first of all, okay, say we'll have in this particular setting. Okay, so we're still working with the XY coordinate system. Now we're not going to be given the specific function. Okay, just going to have sort of a sketch. Okay, so we have in terms of, we say we can have a little bit of a wave pattern. Okay, and just some things to notice. Okay, if you notice with the end behavior at the far end, okay, we have down to the left, and up to the right, and now I can just count up the total number of relative minima and maxima. In other words, like the combined total of peaks and dipping points. Okay, so you got a peak, then a dip, then you have a peak, then you have a minimum, then you have another relative maximum, then we have another relative minimum. Okay, and now just to kind of cue us in terms of the characteristics for this particular polynomial function. Again, we have with the end behavior, once again we have down to the left and up to the right. Okay. Now, the other day we looked at just some of the dynamics, looking at the coefficient and the degree to get to the end behavior, and now we're sort of working in reverse. Okay, so we have with end behavior, notice you have down to the left, up to the right. So what would that correspond with? Well, this will be where we have the leading coefficient is positive and where the degree of the function is odd. So we're going to have here, okay, so for the sign of a of n, okay, so a of n is going to be positive. And again, now the degree n is going to be odd, but now for the sign of a of n, okay, that is going to be positive. Okay, and we have for the number of turning points, those are your combined peaks and dips between the ends. Okay, so we're going to have 6 turning points. Okay, now for the possible degrees of f of x, okay, so n is going to be an odd value. Okay, and in terms of what n is at least going to be, okay, so let me mention regarding the turning points. Again, the number of turning points, okay, will be at most 1 less than the degree of f of x. And again, another way of wording is that the degree of the function will be at least 1 more than the number of turning points. Okay, so in terms of what n can be, when you think of odd numbers, you have like 1, 3, 5, 7, 9. But be careful now, the number of turning points cannot be more than the degree of the function itself. So when you think of like an odd-powered function, okay, if you think of like degree 1 or degree 3 or degree 5, notice, okay, 1, 3, or 5 are all less than the number of turning points, so it cannot be 1, 3, or 5. So the minimum possible degree that this function can be is going to be 7. And if it's not 7, it's going to be 9, and if it's not that, you will have this to be like some other higher odd number, like 11 or 13. Okay, So the value of n could be 7, 9, 11, 13, or any other higher odd power. Okay, so again, you have the n behavior down to the left and up to the right. And again, that is characteristic of a function whose leading term is positive, where the coefficient is positive and where the degree is going to be odd. Okay. And again, with 6 turning points, n could be 7, 9, or any other higher odd power that we have in the mix. All right. Now, if we have, let's say, a case whereupon and still working with the x and y axis and the xy coordinate system in all. And we'll say that we have okay. And if you notice, okay, we have with the n behavior, okay, we're going to have up to the left and up to the right. So when it's talking about n behavior, you're looking at the extreme locations to the left and to the right. So you have up to the left and up to the right. And in terms of the nature of the polynomial, again, if the n behavior is up to the left and up to the right, again, your leading coefficients can be positive and the degree of the polynomial will be even. Now, in terms of what we have for the number of turning points, okay, you're looking at combining the total number of relative minima and maxima. Okay, so you got 1, 2, 3, 4, 5, 6, and 7. Okay, so we have altogether we have 7 turning points. And again, we have that for the possible degrees, we have an n. Now, n is going to be an even value, and it must be a value that is going to be greater than the number of turning points. So for your possible degrees in n, okay, so n is even greater than the number of turning points. So the degree of n, or f of x rather, that we have in n, okay, that's going to be at 8, and the other value is going to be like 10 or any other higher even value. Okay, so this is where we have sort of a tie-in with n behavior as well as number of turning points and the possible degree we will have for the function f of x. All right. And now, looking at what we have in the textbook problems instead of be looking into, and we have for the case in number 48, and we have in the illustration case, so you're going to have a graph whose n behaviors will be up to the left and also to the right, and where we have zeros involved. Okay, so you have the zeros involved. Okay, we have at -4, as well as x equal to -1. Also we have x equal to 3. And just for the way that the graphing is done here, okay, so again we have with the end behavior, okay, we have up to the left and up to the right. And just looking at what we have for the turning points. Okay, so you have relative minimum. Okay, so you have a decrease followed by an increase. And then you have with the maximum, you have increase followed by a decrease. And we have on x is equal to 3. Okay, so you have a third turning point where again you have a decrease followed by an increase. All right, so we have in the setup, okay, so you have with the end behavior, you have up to the left, up to the right. And regarding the sign values, okay, the leading coefficient, okay, so again, up to the left, up to the right, okay, so again, we have that A of n is positive. And for the value of the polynomial, okay, that is going to be an even amount. And we have in the mix, okay, so you have, again, what will be 3 turning points. And again, the degree of the function has to be greater than the number of turning points. Okay, so we have, in this particular case, okay, the minimum possible degree is going to be the smallest number greater than 3. That is even, and that's going to be the number 4. Now for what we have in the second part, this is just a repeat, and it's going to be the sign value of the leading coefficient. Okay, so A of n is going to be positive. Now we have regarding the zeros. Okay, so where we have the graph of f of x to come into contact with the x-axis. Okay, so we have x equal to -4. Also have x equal to -1. And we have x is equal to 3. Okay. And now I'm sort of take things a little bit in reverse, okay, because we had the action already laid out, okay, and in terms of whether we had at each 0 whether the graph is going to cross or touch the x-axis. And whether or not we have odd or even multiplicity. Okay, so for what we have in this particular case, right? So you have x equal to -4. Okay, now the graph is going to cross the x-axis. At x equals -1, it also crosses the x-axis. And at x equals 3, okay, so you have the graph of f of x is above the x-axis, and once it descends to x is equal to 3, it rises back up again, so it essentially bounces off the x-axis, so that would be a case of where it touches. And in terms of odd or even multiplicity, okay, so since the graph crosses at x equals -4, -4 is going to be said to be a 0 that has odd multiplicity. So like the factor corresponding to that could be to the first, third, or fifth power. Likewise for -1, okay, at that location the graph crosses the x-axis. So -1 is going to be a 0 that has odd multiplicity. And for zeros whose location is where the graph is going to touch the x-axis, that corresponding 0 is going to have an even multiplicity. Okay, so again, the function crosses the x-axis at zeros of odd multiplicity, and f of x will touch the x-axis at zeros of even multiplicity. Right. And now, the other day we looked at, expanding and factoring polynomials. And for what we have in the case of 59, okay, we're looking at characteristics of what we have for the function that we have provided as f of x is equal to x cubed minus 5x squared. Okay. And if we look at the end behavior, first of all, okay, so the end behavior, okay, that's going to be contingent upon, okay, the degree of the highest order term as well as the leading coefficient. Okay, so we have, so you can read this as f of x is equal to 1x cubed minus 5x squared. So the leading coefficient, a of n, okay, is equal to 1. So this is going to be positive, and since we have x to the third in the highest order term, we have that n is equal to 3. And 3 is an odd number. So we have with the positive coefficients and the odd power. So we got positive coefficient, odd power. In behavior, we have down to the left and up to the right. Okay, now in terms of activity in between, this is where the zeros will come in, as well as any potential y-intercepts. And all other points in between. Okay, so looking at what we have, again, with the function. Okay, so we got the in behavior. Now looking at what we have for the function, so this is the expanded form. And if I factor what I have here, okay, so we're going to have for x cubed minus 5x squared. Greatest common factor is going to be x squared. And we have times the quantity of x minus 5. And I'm going to do a little bit of color coding to emphasize the degrees. Okay, so here we're going to have x to the second and x minus 5. You don't have any explicit power, so you would read this as x minus 5 raised to the first. All right, and if we look at identifying the zeros and their multiplicities and whether the graph crosses or touches the x-axis at those locations. So we have from x, we have x is equal to 0 from x minus 5. We have that x is equal to 5. Okay, and where the multiplicity is concerned, okay, that's going to determine whether at that 0 the graph is going to cross or touch the x-axis. Okay, so you have with 0, this stems from x, which is raised to the second. So you have a multiplicity of 2, and again, zeros of even multiplicity will be locations where the graph is going to touch the x-axis. So it's going to touch at x is equal to 0, and we have x equal to 5. This stems from x minus 5 raised to the first, so that's going to have a multiplicity of 1, and the graph is going to cross at x is equal to 5. And for what we have with regard to the y-intercept, so we have in this case, right, so the y-intercept you're looking at solving for y as x is set to 0. So you're going to have that y is equal to f of 0. Again, so we have 0 to the third minus 5 times 0 squared. And again, when we have these values will become negligible. So we have for the y-intercept, okay, have now y is equal to 0, and in coordinate terms, okay, we'll end up at the origin. So looking at what we have, in terms of the sketching of what we have for this function f of x. Okay. Again, we have with our zeros. Okay, so you have x equal to 0 and x equal to 5. And just doing a little bit of labeling here. So we have x equal to 0, x equal to 5. Okay, now just stressing the end behavior. So you have 0 is the leftmost 0, 5 is the rightmost 0. End behavior you have down to the left. And we have at the other end, we have up and to the right. Okay, so this is what we have for the extreme ends, down to the left and up to the right. And for what we have at 0 and 5. Okay, so at 0 the graph touches, at 5 the graph is going to cross. So just filling in the gap here. Okay, so you have reading from left to right. So you have beneath the x-axis, and once we get to the origin, the graph is going to touch. It is kind of bounce off the x-axis. Then the graph is going to start to, after going down, it's going to go back up. And once we get to x is equal to 5, the graph is going to cross the x-axis, and the rest of the activity that we have here for f of x is that it's going to go continuously up and out to the right. All right. And now for what we have in the case of the next item, and we have some similarities, and we have in the case of number 60, we're going to have another odd-powered function. Okay, so what I have here, okay, we have a function g of x g of x. Okay, so you have g of x, okay, so you have equal to x to the 5th minus 2 times x to the 4th. Okay, and if we go ahead and tackle the end behavior, again, the leading coefficient is going to be at 1. So this is going to be positive. Again, x to the 5th is a higher order term, so the degree we have, again, to be an odd power. So you had the combination, have a positive leading coefficient, and the degree of the function is odd. So you're going to have the same end behavior once again, where you have down to the left and up to the right. And looking at the x-intercepts, or the zeros, of this function. So again, we have g of x is equal to x to the 5th minus 2 times x to the 4th. And here we have the greatest common factor, which we will have at x to the 4th. And factoring, we have x to the 4th times the quantity of x minus 2. Okay, so just stressing the exponents. Okay, so you have g of x. Okay, so you have x to the 4th. Again, we have times the quantity of x minus 2. And this will be to the 1st. Okay, so you have with the zeros, so we have the x factors at the letter x and the binomial x minus 2. So here we have x equal to 0 and x equal to 2. You got your multiplicity, and also whether the graph is going to cross or touch the x-axis. Okay, so we have x equal to 0. Okay, 0 stems from x, which is raised to the 4th. And anything that has an even value multiplicity, at that location, the graph is going to touch at that 0. So it's going to touch at x is equal to 0. For x is equal to 2, this stems from x minus 2, which is raised to the 1st. So 2 has a multiplicity of 1. And for those zeros with odd multiplicity value, the graph is going to cross. And again, for the y-intercept, and for this one case, we will have y is equal to g of x, and as x is set to 0. So you have g of 0. So this will be 0 to the 5th minus 2 times 0 to the 4th. And both of these are going to be negligible. So y is equal to 0. And in the case of the y-intercept, y is equal to 0. And again, you can just put this in coordinate fashion where the location is going to be the origin. So just looking at what we have here. Okay, so we have with the zeros. Okay, so we have it 0 and 2. And starting out, okay, so if I have the end behavior, again, we have down to the left and up to the right. Again, we have our zeros. We have x equal to 0, x equal to 2, and the y-intercept is at the origin. Okay, so the x and the y-intercept at x equals 0, again, it's going to be the origin, the one, and the same point. Now, for x is equal to 0, okay, now the graph is going to touch the x-axis, whereas at x is equal to 2, okay, the graph is going to cross. And so just looking at what we have here, so at 0 the graph is going to touch, so it's going to bounce off the x-axis, then it's going to increase, and once we get x is equal to 2, okay, the function is going to cross the x-axis at x is equal to 2, and the rest of the activity is going to be up and out to the right. All right, now for what we have now, just doing a little bit of a change up, and we have for number 64. Okay, this time we're going to have going from f to g to now h of x. And there will be 3 terms in the mix, whereupon we have h of x is equal to x to the 4th minus x cubed minus 6x squared. So again, we have the leading coefficient. It's going to be at 1. So that is going to be positive. Now the highest order term is x to the 4th. So the degree of the polynomial is going to be 4, and 4 is an even number. And with a combination of a positive leading coefficient along with an even power, okay, this signals that the end behavior is going to be up to the left and up to the right. And in terms of the x and the y intercepts, okay, so you have with this polynomial, again, if I'm looking at factoring, okay, and the greatest common factor here, okay, we have all of these to be variable terms, and they are raised in the order for the variable x, and the greatest common factor is going to be at x squared here we have x squared times the quantity. So we have x squared minus x minus 6. And then we have upon factoring further. Okay, so again, we already have x. Okay, so this is going to be to the second. And for x squared minus x minus 6, and we have x plus 2. on the side of addition, and for what we have on the side of subtraction. So we have x minus 3, and both x plus 2 and x minus 3, okay, those will be a first degree. And in the case of the zeros, that's the x-intercepts. Okay, so I have from x, I have x equal to 0. From x plus 2, I have x equal to negative 2. And from x minus 3, okay, so I have x is equal to 3. And for the multiplicities, okay, so 0 stems from x to the second. And negative 2 and 3 stem from first order factors, so their multiplicity will each be at 1. And in terms of whether the graph is going to cross or touch, the x-axis, okay, so with a multiplicity of 2, even multiplicity signals that the graph is going to touch at that 0. So in this case, so it's going to touch at x is equal to 0. And with negative 2, that has a multiplicity of 1. So it's going to cross at x is equal to negative 2. And it's going to cross at x is equal to 3. And in the case of the y-intercept, okay, so you have y is equal to h of 0. And we're going to end up with a trio of negligible terms. So this bit of history is going to repeat. So we have for the y-intercept, okay, so you have y is equal to 0. And once again, in coordinate fashion, okay, this will be the origin. So just looking at what we have in labeling and sketching. Okay, so we got our zeros. They have 0, negative 2, and 3. And we have, again, just that with the end behavior. Okay, so you have up to the left. So you have up to the left from the leftmost 0. And we have at the other end, we have up to the right. This is up to the right from the rightmost 0. And for the activity in between, okay, so you have touching at x is equal to 0. And at negative 2 and positive 3, okay, now the graph is going to cross. And again, the y-intercept we have at the origin. Okay, so and looking at what we have here, reading in order from left to right, so we have the graph is going down. And we have crossing at x is equal to negative 2, then it rises up. And at the origin, the graph is going to touch. So it's going to bounce off the x-axis, then it's going to descend, and then it's going to rise back up again. And once we get to x is equal to 3, the graph is going to cross. And so this will be essentially the nature of the behavior for what we have regarding h of x. So you have the end behavior, and also crossing at x equals negative 2 and x equals 3, and touching in the central location at the origin. And right now we've had so far the y-intercept to be at the origin, and there's going to be a change up in the case of what we have with number 72. And for this particular function, okay, so you have a function h of x, and that is equal to negative x to the fourth plus 10x squared minus 9. Okay, so if we look at the end behavior, okay, first of all, we have the negative of x to the fourth. So a of n is equal to minus 1. Okay, so this is going to be negative. And we have for the degree n is equal to 4. Okay, so 4 is going to be an even value. Okay, and so have a negative leading coefficient, and the degree is even. And in this scenario, okay, now the end behavior, we have moving down at both ends, down to the left and down to the right. And where the zeros are concerned, okay, so you have, again, with this particular trinomial, okay, now what I can do here in order to make this factor friendly is I can factor out the negative that is in front of x to the fourth. Just say I have negative 1 times the quantity. You have x to the fourth minus 10x squared plus 9. Again, so upon factoring out negative 1, I can now factor the trinomial x to the fourth minus 10x squared plus 9. And here, I'm going to have differences of squares factored out. From x to the fourth, I'm going to have x squared and x squared, and factors of positive 9 that will add up to negative 10. And we have a minus 9 and a minus 1. And for x squared minus 9, okay, I have with this difference of squares, we have x plus 3 and x minus 3. From x squared minus 1, we have x plus 1 and x minus 1. And all of these will be a first degree. So you have with the zeros. Okay, so you have with the variable factors. Now, again, negative 1 is just a coefficient. Doesn't have anything to do with finding the zeros of the x expressions. Now from x plus 3, we have x equals negative 3. From x minus 3, I have x is equal to 3. From x plus 1, if I set this equal to 0, I have that x is equal to negative 1. And if x minus 1 is equal to 0, I have x is equal to 1. And regarding the multiplicities, again, so we have all of these zeros, okay, come from factors that are of first order. So these multiplicities, okay, all of these will be at 1. And so since we have exclusively odd valued multiplicities, okay, you're going to have the only activity for the zeros is that you're going to have to cross the x-axis at all 4 of these zeros. Okay, so it's going to cross at x equals -3, x equals 3, x equals -1, and x is equal to 1. Now for the y-intercept, okay, this is no longer going to be situated at the origin. Okay, say y is equal to h of 0. So we have the negative of 0 to the 4th plus 10 times 0 squared, followed by the subtraction of 9. So these terms will be negligible. So we have that y is equal to -9. So for the y-intercept, we have at y equals -9, and in terms of ordered pairs, okay, we have at 0, -9. So looking at it through the lens of a graphing display, again, we have with our zeros, okay, on the x-axis, we're going to have -3, -1, +1, and +3. And again, I have a y-intercept at 0, -9. So we're going to have 5 intercepts altogether, 4 on the x-axis and 1 on the y. And again, we have at all of these values on the x-axis. Okay, we have the graph is going to cross the x-axis. And we have in terms of the behavior of the graph, again, we have down to the left and down to the right. So you have taking the leftmost 0, again, we have down to the left. And the rightmost 0, okay, so again, we have down to the right. And just for the activity, okay, so starting from left to right, so we have at -3, you have cross, it's going to rise, you have to descend, so you have crossing at x is equal to -1, and it's going to go through the y-intercept and go back up, and it's going to cross above, then it's going to fall, and once we get to x equals -3, okay, it's going to cross, and the rest of the activity for what we have for h of x, again, we have moving downward and to the right continuously. So that will be what we have in terms of the general behavior concerning this function that we have for h of x. All right. Now the other day, okay, we looked at forming factored and expanded polynomials from given zeros, and there are just a couple more cases I want to give, especially one that has non-integers in the mix. And in the case of forming polynomials from given zeros and multiplicities, Now let's say if we have in this one, okay, say we have determine an expanded form of f of x given, okay, I'll say that for the first polynomial f of x, let's say we have zeros. Let's say we have 0, which will have a multiplicity of 3. And we'll say we have with the other, okay, we'll say we have -4. I say this will have a multiplicity of 2. Okay, so we'll let these be our only zeros. Okay, so, and the degree will be the sum of those multiplicities. Okay, so this is going to be at 5. Okay. And if we look at taking what we have here, so for an expanded form of f of x, we can start out with a factored form. So corresponding to 0 and -4. Okay, we have with our factors. Okay, we'll have, again, let me sort of lay the groundwork here. Okay, so we have with 0, okay, we have x, multiplicity of 3. So you have not just x, but x to the third. With -4, we can say that comes from x plus 4. And since -4 has a multiplicity of 2, this is going to signal that the corresponding factor will be raised to the second power. So starting out with the factored form, we can say we have f of x is equal to x cubed times the square of x plus 4. And for following through, getting into the expanded form, you could go ahead and square out x plus 4 and say x cubed all over x squared plus 8x plus 16. Another possible way is to rewrite the square of x plus 4 is x plus 4 times itself, and then you can just multiply the factors in order from left to right. All right, so we have here, okay, so you have x cubed times x plus 4 times itself. So if I multiply or distribute x cubed over the first of x plus 4, so I'm going to have x to the 4th plus 4x cubed we have times the quantity of x plus 4. And taking what we have in the FOIL, okay, so you have x to the 4th times x. So that'll be x to the 5th. Outside product, okay, we'll have it 4x to the 4th. Inside product is also going to be at 4x to the 4th. And the last product, okay, that is going to be 4x cubed times 4. So this will be at 16x cubed. Okay, and the result again is going to be a 5th degree polynomial. So we're going to have x to the 5th plus 8x to the 4th plus 16x cubed. So this would be an expanded form of a polynomial that will have those zeros and their multiplicities, and where we have, once again, where the degree is going to be at 5. Now, let's say that if you have non-integers in the mix, and we'll say that we have say we have with our zeros. Okay, we'll say we have, we'll just let these be a multiplicity 1. Okay, now we just have the degree of the polynomial to be at 2. So you got negative 2/3 and 4/5. Okay. Now I'll show you two approaches here. There'll be distinct polynomials where one's just going to be a multiple of the other. We say that negative 2/3, x equals negative 2/3, will stem from x plus 2/3. Now we'll say that we have x equals 4/5. This will stem from x minus 4/5. Okay, let's say as an option, you can remove the fractions. You can remove the fractions in this exercise. And what I mean by this, okay, say if I get out of the thirds as well as the fifths, what I can do here is that for the first factor, I can multiply by 3. And with the second factor, okay, which we have a fraction in fifths, I can just multiply this second factor by 5. And if I go with this route, think of it like this: 3 times the quantity of x plus 2/3. This would be 3x plus 2. And 5 distributed over the quantity of x minus 4/5, and we have 5x minus 4. Again, if I were to set 3x plus 2 equal to 0, 3x would be negative 2, and x would come out to negative 2/3. And if I have 5x minus 4 equal to 0, I would have 5x is equal to 4, and x would be at 4/5. So it's not going to change the zeros at all. And so, looking at foiling out, so if I take the first product, okay, so you got 3x times 5x, so we have at 15x squared. Again, we have minus 12x. We have plus 10x. Minus 8. So one version of the expanded form, here we have f of x is equal to 15x squared minus 2x minus 8. Okay. And another version, okay, if you were to keep the fractions and just take the FOIL with the terms we have at face value. Okay, so I have x squared. And what's going to be minus 4/5 of x plus 2/3 of x, and 2/3 times negative 4/5, this will be a minus 8/15. And if I adjust the fractions to where I can combine the like terms now with negative 4/5 and 2/3, now the least common denominator is going to be at 15. So if I write 4/15 or 4/5 a fraction over 15, so this will be minus 12/15 of x. And 2/3 is going to be 10/15. So another possible expanded form, okay, we're going to have a f of x is equal to x squared and negative 4/5 of x plus 2/3 of x. Once we convert to 15ths, that is going to leave us with negative 2/15 of x. Minus 8/15. Right. So those are two ways you can go about arriving at a polynomial in expanded form that even if you were to factor, you would have the very same zeros, and where the degree is still going to be of second order. All right, and now just some items, and we have concerning operations. Okay, we've been looking at combining like terms, multiplying, and now in the crossover to what we have in the next part, and this is what we will have with polynomial division. And in the case polynomial division, let's give you a couple of examples here. If you have, let's say, if we have x squared plus 4x plus 9 divided by x minus 2. Okay, I'm just writing as a ratio. So you have x squared plus 4x plus 9 over x minus 2. Now, there are a couple of modes of polynomial division we will look into. And the first is going to be in the case of long division. And in the case of long division, okay, so I'm taking x minus 2 into x squared plus 4x plus 9 okay, so I have both x minus 2 and x squared plus 4x plus 9 in descending degree order. Okay, and what I'm going to do here, looking at the first term is x and x squared. Okay, I pose the question, how many times will x go into x squared? Or what is x squared divided by x? That is going to leave us with x. And you're going to distribute this x over x minus 2. So just kind of stepping to the side here. Okay, so I have x squared minus 2x, and I'm going to take this product, x times x minus 2. I'm going to take x squared and negative 2x, and situate each of these terms underneath the like terms from the top. So in the case of what we have here, long division will be a process of where we have going using row by row subtraction. So the object is going to be to from the dividend, we're going to try to cancel out the x squared, so we're going to subtract, so x squareds will go out. Now we have with the first order x terms, we have 4x minus negative 2x, so we have 4x plus 2x is going to be 6x, and then with the 9 we can bring that down. Now we took x into x squared, and after the first round of long division I got 6x as the front term. So for x into 6x, this will go 6 times. Okay, just to mention, so you have 6 times the quantity of x minus 2. You have 6x minus 12, and we'll take that product and just take each term and place under the corresponding like term what I had after the first round of long division. So applying subtraction once again. So you have 6x minus 6x will go out, and we got 9 minus negative 12, and that is going to leave us with 9 plus 12, so this is going to be at 21. So for what we're going to have for the features here, just some of the terminologies. Now the divisor, okay, that's what you're using to take into, so, or what you're dividing by. So the divisor is going to be x minus 2, and the dividend, what you're taking into. Again, that's going to be x squared plus 4x plus 9. And now for the quotient. For the quotient, okay, that's going to be x plus 6. And we have with the number 21. Okay, so that is going to be the remainder. And we have with just this other case here. Say if I have x cubed plus 4x squared plus 5. And you say have all over x plus 1. So if I perform long division, so I have x plus 1. Now for the dividend, I do not want any missing degree terms. Okay, so I got x cubed, and I got plus 4x squared. Notice that the next term is 5 as opposed to an x term. So what I need to do here is use a 0 placeholder. So I have plus 0x. Yeah, followed by the addition of 5. So just looking at, like we took x into x squared, I'm now going to take x into x cubed, which will go x squared times. Again, just to kind of state here, we have x squared times the quantity of x plus 1. So you have x cubed plus x squared. So again, you have x cubed plus x squared and subtracting x cubed will go out. Now we got 4x squared minus x squared, so this will leave us with 3x squared. And we can bring down the 0x and the 5. Then for the next, we have x into 3x squared. 3x squared divided by x is going to leave us with 3x. And if you can see the distribution right away, that's fine. But 3x times x plus 1, this will be 3x squared plus 3x. And just taking this under the like terms, so you got 3x squared plus 3x. And subtracting, so 3x squares will go out, and we have 0 minus 3x, so we have negative 3x plus 5. And x will go into negative 3x minus 3 times. So that'll be negative 3x minus 3. And subtracting once more. So we have negative 3x and what's going to be plus 3x, those will go out, and we have 5 minus negative 3, which will be 5 plus 3, and so that is going to be at 8. Okay, so for what we have here, again, we have with the divisor, again, that's going to be x plus 1. And in the case of what we have with the dividend, okay, so you have x cubed plus 4x squared plus 5. And for the quotient, okay, that's how many times it'll go into without going over. So the quotient, that's going to be x squared plus 3x minus 3. And for 8, we cannot take x plus 1 into 8, so 8, that's going to wind up as the remainder.